Swayam Prabha. Digital India. Educated India.
Good morning everyone. Okay, I welcome you all to this session. We'll be discussing about moorings, types, design and analysis. In the last couple of days we were intensively talking about wave energy converters, right, in the near shore and also in the offshore regions. So we in this lecture will be having these contents. We'll have the moorings. First we'll discuss why mooring is required, what is a mooring, and how to design a mooring, right, and how to analyze it. And to make it little interesting, we'll all have a derivation of an inelastic mooring line and why it is very important and how to solve it. So finally we are interested in solving the problem, right, not just discussing the just equations. So how a physical problem, when you have it, you convert to a mathematical sense and apply some method to solve it, right. This is one way to get started. So this is not a complete part of the mooring itself. We just start with it, but then a series of lectures are required in order to discuss more, right, to get into the sophisticated tool development. But then this is an introductory class, so we'll have on moorings and why, and all those contents wise we'll keep going. And why mooring? So before we get into why mooring is required, so in the last couple of classes, as we saw, a lot of wave energy converters we have been talking about. Depending on the types, you can see that oscillating type accounts for 78% worldwide, correct, and OWC, which is nearshore one, and submerged pressure differential overtopping devices. So it is very evident that oscillating type is much preferred, and presently on the worldwide sense it is 78%, right. And based on the location, if you see at the bottom, the offshore scenario basically 64%. So almost all of the floating wave energy converters and even your offshore structure, everything is on the offshore, right. So 64% it is offshore and nearshore as well, considering the OWCs and other aspects, and there is always a transition from the nearshore to the offshore and in between regions, right, and the onshore regions as well. So at the end of this lecture, I expect everybody to know what is a mooring, why it is required, how to design it, analyze it, and if somebody gives an less inputs, how to start designing it, right. You should be able to get some reasonable numbers and it should lead to a better path. So offshore moorings, the fundamental role of a mooring is station keeping the floating structure. So they are, I would say it is they are all the unsung heroes. Basically, many of the time when you see a floating structure, you don't see the mooring, right, which is just like a duck, the legs you don't see it, but that is what is helping us to keep it going, correct. The same way, the moorings, the primary aim is to station keep it. When we say station keep it, it is to keep it in place, right, but not so restrictively, right, but then it is little complex and it can go around a particular. So I have a nice analogy figure in the next slide, so that can give a good clarity and keep intact. So moorings are an integral part of any offshore activity, not for any of the activities, so, right, for offshore drilling, starting from offshore drilling, production, transportation, maintenance, floating, offshore wind turbines, and also the wave energy converters. So in the last couple of we have spoken more about the wave energy converters and how a physical problem is transferred, and we are mostly talking about the body interactions and setting up the equation of motion, basically, correct, but nowhere we are talking about the moorings coming in picture and its contribution to the overall response, right. So in this lecture we will be focusing there, and designing a mooring system is difficult due to the challenges involved. The various challenges are the site conditions, because as you start from the your shore to going to the offshore region, so the water depth is constantly changing, correct. So depending on the site conditions and the metocean data, what is the wave height at that time, at that location, what is the time period at that location, what is the current, the last session also we were talking about the currents, right. So it depends on couple of parameters which you can see, and the challenges also there. An analogy, so just for keeping us ground here, So this is what we might have seen in our villages, wherein you have a cow, you have a rope which is tied, right? Basically here when we say a cow, basically we are restricting its motion, right? We are restricting it to go around a particular point, correct? So in the same way for our floating structures as well, for your mooring, one end is connected to the floating structure, the other end is connected to the seabed, right? And how you make a connection and what are the different compositions of this, right? For example, in the same figure you can see a wire rope is given. For example, if you put a chain of a very bigger size, your cow cannot take the load, correct? So all these, so depending on what type of structure you handle, your composition of your mooring also will play a role, right? Okay, so now we understand that during its course of time, a floater excursus basically we mean that it will move around, right, during its service. So mooring lines are constantly changing their positions as a function of time, right? It is understandable. So that is what we call as a watch circle. So watch circle is the extent to which it can basically go and the circle that it basically forms. The watch circle is the floater's excursion from the mean position, right? For example, you can see on the right side you have a drilling rig and you have a riser. So generally for drilling operations we don't use moorings, we have a separate another item, basically the dynamic positioning system, wherein you bring in the thrusters to keep it in place. So either by having thrusters or by moorings you restrain the structure in the place. So that's what we mean, right? So to station keep a floating structure we can use mooring or a dynamic positioning system. So depending on the type of application, whether you want to go for drilling, whether you want to go for production activity. For production activity, when we say it, basically for 20-25 years is the service life, right? You start doing, it's like constructing a home, 6 months hardly, right? So the drilling operation also generally happens for 6 months. After that, for next 20-25 years you are going to stay there, or you are going to start doing all your operations and you start extracting your oil or hydrocarbons basically, right? So for these kind of drilling operations the dynamic positioning system is used because you wanted it to be very precise in place, correct? So for which you are inputting some power, right? Whereas for a mooring system you don't need any power to be supplied, you just connect some kind of a wire rope or depending on what water depth you are handling, right? So depending on the type of operation, dynamic positioning system comes in picture, and for a type of operation. So since sophisticated sensors and power requirements exist with the DP, they are often chosen only for specific cases such as drilling operations. So that's what we say. But there are some places wherein the combinations with dynamic positioning, you also have a mooring, right? So depending on the type of requirement, and all these things are site specific activities, right? Okay, so some pictures for interesting things. So it is not always that you have simple catenary mooring or any one, but then they also come in combinations. So that's what we wanted to say, and the reference is also given here. So just a quick comparison, dynamic positioning system with the moorings. So for the dynamic positioning systems we said we have some thrusters which is going to keep it in place, right? So basically it is like it senses your direction of wave and also the wind direction and all those inputs it takes in consideration, based on which the thrusters will adjust the power such that it will stay in place, right? So here now we understand that for any offshore structure we have the environmental loads, basically the wind, wave and current, right? And you have a floater, and for a mooring basically one end is connected to your floater, the other end is connected to the seabed. So the one which is connected to the floater is what we call as a fair lead, basically the top point, right? So the fair lead, and the other end which will touch the seabed and it will run few kilometers on the seabed or few meters on the seabed, and then it will terminate with the anchor, right? So that is how it is generally done. So the mooring limits the floater's excursion to ensure the safety of other systems, because when you are dealing with a floater, it is not just your floater alone, right? So for example, you have an oil and gas platform. So it is not just the moorings alone, it is primarily aimed at having other risers and umbilicals to take in picture, correct? So they have some limitations, because of which your floater, though it can go little bit forward, it can excurse, but then it is restrained, right? Okay, the moorings are generally designed for various conditions, from harsh environments like the North Sea to mild environments. So like the Gulf of Thailand or offshore West Africa. So all we say that basically different regions has a different metocean data. So based on which only the moorings are selected. So as of now we know that what is a mooring and why it is required, right? Moorings are primarily meant for station keeping, and the design basically depends on where it has to operate, correct? So the mooring times are based on the following, and also whether you are going to have for a shorter time or for a longer time duration, correct? And also the profile, whether you want to have a catenary mooring, taut mooring. So it is basically an iterative process. We don't stick to any one. You start with one. You start with one set of physical parameters, right? Then you iterate it, right? Profile wise, we have the catenary and a taut, and also there is one more semi taut. System requirements as well, the spread and single point mooring. So mooring type based on the profile, you can see that catenary versus taut moorings. So for shallow waters, much of the time you see a catenary mooring, right? So when you have a floater and there is a set of lines which is running from your floater to the seabed. So why it is taking a catenary shape? So we are saying that when I am just going to hold some kind of a line here, for example this line, right? So basically it is taking some shape, correct? So why is that? Because of the self weight, right? Because of the self weight. But in case of these things are already submerged in water, right? Completely. So it is basically the submerged weight in water, because of which you are getting the catenary shape, right? And what is called an anchor footprint. So now we discussed about watch circle, which means that it can, as the cow can go around that point, correct? And where it is connected, the end A is connected to the floater, the end B is connected to the seabed, and it is all connected. If you see it in a plan view, you basically have some circle, right? What we call as a anchor footprint, right? Okay, so now there are a lot of new terms coming up: watch circle, anchor circle, right? And what has to be the composition of it, right? And how to choose all these things. So that is a question now, right? We have a lot of things to play with, right? And whatever you choose is a correct one or not, we actually don't know, right? We start with some physical parameters, then you go for iteration, then you say that it is satisfying my all the requirements, right? And it is also cost effective. Finally at the end of the day, what we want to invest less but no compromise in the performance, correct or not? Whenever you purchase a product, the same mindset, correct? You want to invest less, but then the performance should be great enough, right? The same procedure goes in the mooring design and analysis as well. So now we will quickly see what are the different types and why different types are there, and on what basis you choose this, right? So spread versus the single point mooring. So spread mooring generally for the permanent, when we say permanent, nothing is permanent basically, correct? So the 20 to 25 years service life, that's what we call as a permanent activity. So typically how many moorings will be there for a semi-submersible? For example, let us take, you are aware of the semi-submersibles, right? So basically a floating structure with having columns and pontoons, right? So let us take, I think this will, okay. So if you have a 4 cross, let us take 4 columns are there, right? So for example, okay, let me put it in the plan view. So so this is basically your columns, correct, in the plan view. And now if I don't have any moorings, over a period of time they get drifted off. So I need to have some moorings in place, right? So now how to put a mooring here? So that's a straight question. So when a layman starts thinking, the same way we initiate, but then we refine it, correct? So now either I can have 1 or 2 moorings per column, correct? So if I am going to have only one, so it will be 4 cross 1, right? 4 columns, 1 per column, that I can have. Or I can have 4 cross 2, 4 cross 3, so depending on the requirement. So what will happen if I am going to travel this way, 4 cross 1 to 4 cross 3? If I am going to have 4 cross 3, it will have better performance, right? Because you have 3 moorings running. But then what is the disadvantage? Because you might have invested more, right? Okay, so now we will revert back to 4 cross 2, right? Whether I can use 4 cross 1, that's a question now, right? If there is 4 cross 1, so if for example assuming that you have only one mooring line per column. If that gets damaged, right, there will be a greater offset, the excursion will be high enough. So we cannot choose 4x1 as well, right, we cannot go for higher number of moorings as well, correct. So we have to start with some number, then slowly refine it, right. So that's how it is generally done. Okay, so this is for spread mooring. Basically you are spreading over your complete structure, correct. So this is basically a spread moor, right, spread mooring. Whatever we are doing here is a spread mooring. So single point mooring, when we say it, there will be for your floater, the connections will all be made to that particular point only, right. For example, you have a, say all these things I am putting in the plan view. So let us take, this is a ship in the plan view, right, and this ship, there will be some connections which is outside it, right, and all the connections will be made to this particular point only. So this is a single point mooring. So right, your floater connected to a single point only, right. So we will see some figures, so that can give some quick clarity. So all these things are single point mooring, correct. So you can see your floater, basically you have a floater and this is connected to a, and only a single point connections is there, correct. So this is also a single point mooring, correct. So in that there are two types, basically external turret and internal turret. So what is the advantage by going for a turret system? Basically it will help you for weather vaning. So when we say weather vaning, so basically you have a floater, right, and assuming that your connections are made here, right, and now the direction of wind and wave comes in this direction. What will happen? This will slowly align its position, right. So now, so in the direction of your wind and wave, it will align itself, right. It don't need to take all the load, it can bypass it, it can leave it aside. So this is what we call it as the weather vaning. So these things, this single point mooring is much preferred for ship shaped vessels, right. So the weather vaning fundamental idea is that to reduce the impact of the environmental load on your floater, whereas in case of your spread moor, whether you like it or not, the environmental loads will continue to persist on the structure, right. So now this turret system can be outside or within the vessel itself, correct. So what we call as the external. So in this case whatever you are seeing is the external, right, it is outside your ship. So what is the advantage? Since it is outside, it is above the water surface, if there is any repair and maintenance activities to be done, it can be done quicker, which may not be possible if it has to be within the vessel, wherein it will take extra space as well, correct. If it is within your vessel, assuming that it is within your vessel, it has to, you need to provide dedicated space for it, correct. So that is a disadvantage with the internal turret. Much of the time you see in the real world the people adopting the external turret system, right. So this is also an external turret system, right. So then so how this is staying in place? So now the question, so you can see that moorings are outside, right, this is a single point mooring we say, basically, correct, it is outside, all these things are outside, correct. Okay, so till now we did not say how a mooring is being made, whether it is a chain, wire rope or polyester rope, we did not talk about, we will come back to that, correct, we did not speak that. We say mooring is some kind of a line element which is helping us keeping your floater in the place. So that is what we are talking about. Okay. So all these things, some figures for quick catch. So this is also an external turret. So now this is an internal turret, right, arrangement in an internal turret. So as we said, for an internal turret you need to have a dedicated space, right, and also a lot of complex systems come in picture, correct, because it has to allow for the swiveling of your floating body. When we say weather vaning, we basically mean that swiveling of your floating structure so that it will align to the direction of wave, right. Okay, so this is an internal turret system. You can see a lot of bearing systems and other things which is coming within your floating system itself. Okay, so this is so all these pictures basically from your DNV course, I will give the reference so you can have a look at it. Okay, so when we have this kind of a system, it can be either submerged, right, or it can be emerged as well, right, and it can be disconnectable as well, right. For example, when you are having a harsh environment coming up. For example, next 2 weeks the weather forecast says that some inclement weather is there. So what you do, you want to evacuate the place, correct? So quickly I will disconnect from the system, I leave it in place so that this has some kind of a buoy, right? This buoy will try to, in the water line you have some kind of a buoy, right? This will try to go up, whereas your chains which is connected to it will try to pull it down. So they will come to some equilibrium position and they will be there. So once the weather subsidizes, after 2 weeks, cyclone or whatever is being gone, they will come back to the same site and they will use some kind of a messenger wire to pull it back and make a contact with it, so that it will stay in the required place. Okay. So this is the disconnectable turret. So you can see in the event of harsh environments, they will disconnect it, they will evacuate the place. Once it subsidizes, they will come back to the same place and they will use a messenger wire to make a connection to the floater again. These are some of the variants we have, the disconnectable turret system. So all these things are disconnectable. Okay, so now we understand that external, so depending on, so what to choose, so that's a question. So external turret system has several advantages, such as standalone fabrication and installation are done along the quay side, and also the internal turret system can only be installed in the dry dock. So these things will add up to the cost, overall cost of the project, right? When we have a, when you take a project, we try to see the items to give optimal performance, right? The best performance, but then with minimal investment. So that is the thought process with which the client also approaches. The storage capacity of the hull is not affected. So in case of a external turret system, right? Almost all external turret systems are raised above the water line, so inspecting and maintenance will be easy. So that's what we said. So just a summary. So and again different types exist. The catenary anchor leg mooring system, wherein you have a, so a buoy is there. So this will be connected with a lot of mooring chains, and some kind, many of the times if you go to the port, you happen to see few vessels, we don't bring it to the port, we try to deal with them outside the port itself, right? For example, you have an LNG, you generally don't let them in the port, right? You keep them off. The reason is, first thing, it is highly inflammable, you don't want to take any risk, right? You want to keep them off the port, right? In such scenarios, what are the different items that you comes in picture? So the selections could be either the calm or the single anchor leg mooring, right? So you can also see some kind of a pipeline. So you can see the pipelines with some kind of a buoys connected, basically to let a connection. So wherein you have some kind of a pipeline end termination, then it will travel all the way to the shore. Correct. So some of the items here. So basically is the storage tanker. You can see. And also if your floater is or your ship shape or your vessel is very big in size, you cannot bring inside the port because your turning circle, right, turning radius will restrict it, correct? Okay. And differential differential compliance, whether we are saying about spread mooring or the single point mooring, not necessarily we have to always stick to that. Many of the times, for example, you are developing a particular site, for example we purchase a land, other things. So they all get developed over a period of time, correct? So for example, you have a ship shaped vessel, right? You will not have the loading uniform throughout, right? For example, lot of risers will run from one side, the other side will be empty, correct? So in such a case, I cannot go for a spread mooring, right? So in that case, I have to be little biased, because this will, all these risers will try to pull it down, or there will be a tilt happening to the vessel. So in such a case, I need to have a differential compliance. So wherein one side more number of mooring lines will be there, on the other side less number of moorings also will be there. Okay. So now the mooring design basically is an iterative activity, that's what we said. So now we understand there exist a lot of parameters that we have to take in consideration before you start designing, right? First thing is, get a clear information from the client, what needs to be done, right? Collect project information and also where it is going to operate, environmental conditions, and create load cases. What is the maximum load, maximum wave height and time period that will be coming during its service life, right? That's what you do whenever you are going. So how much expense, you will always be prepared, correct? So all these informations are required to design your mooring properly. And also we carry out hydrodynamic analysis of the floater, because as your floater is going to, for example, you have a floater which is going to have a natural period matching the site natural period, right? Site the most probable wave period. Let us take for a given site you have a most probable wave period as 15 seconds, and if your floating body natural period is also 15 seconds, right? Then they will always be in resonance, right? It will always behave very violently, correct? So you must have the hydrodynamic analysis done priori so that you will know how to position them, right? Because that comes as an input, because all your moorings are connected to your floater. When your vessel is going to move, that is going to transfer the load to your mooring, correct, and it is going to travel all the way to your seabed as well. So depending on your floating body also. Carry out mooring analysis on the preliminary design, check for compliance using the codes. So whatever we do, we have to comply with the code. So this is a standard procedure for all engineering activities. Whenever you are designing something, it has to comply with the code. So the code books are nothing but the compilation of the past experiences. What are the do's and don'ts? So in simple terms, what are the do's and don'ts is what a code book says. Restricted. So sometimes you will see a lot of empirical relation, 1.5, 3.5. If you ask that number where it comes, basically based on the past experiences, correct? So it has been based on joint industry practices with the different companies, it will all evolve and it has been summarized, right? So it has to comply with the code. And selecting the mooring components and equipment, right? Okay, so now the mooring design process. So as of now we are saying mooring is required. So now we understand the importance of mooring. Mooring is really required to keep your floater in place, but then to make a selection where a lot of other parameters has to be taken in consideration. That's what we saw. Till now we did not get into what is the composition, what are the other things coming in picture, and what sort of loading comes in picture as well, right? So we will see here. So the design process of a mooring system depends on the following. So the mooring system, first thing you will select whether it is a spread mooring or a single point mooring, right? And then your profile, because if you are going to have a catenary mooring, you will have a larger excursion, right? But then the advantage is that you don't need to worry about the selection of your anchors, because it is very far from your touchdown point where it is going to make contact. So there is always a trade-off. If something is going to be good, it will have an impact on the other, right? So for example, if you have a catenary mooring, you need to have a very larger length, right? So you are going to invest more. So in case of a taut moor, you will have a very shorter length. But then what is the disadvantage? You need to make sure the point on the seabed has a very good connection. It should not come out, correct? So there is always a trade-off between the different quantities that we talk about. And then the mooring pattern, what should be the anchor radius, and how many number of lines that I have to choose, whether I have to go for 4x1, 4x2, 4x3, right? And also the spread angles, we also put the angle between the line, correct? So what should be the angle between them? So mooring line composition, for example, if the water depth is 10 meter, you can hold some chain or something, correct? But if your water depth is around 1000 meters, even you cannot do anything. I mean, the top tension will be very high, correct? So we need to have a different composition in that case, correct? We will see that. And what has to be the type of anchor on board equipment. Okay, so now you can see the bottom figure how the operation has fared over the centuries, I mean over the decades, from starting from 1940s, 1950s, slowly it has increased. So you can see exponentially the number of floating structures has increased, correct? So these many structures are operating in the deeper water and ultra deeper water, right? When they are operating, definitely moorings are there, correct? And there is some set of activities they are doing it, right? So that is the importance of the mooring. And what is to be selected, whether the catenary mooring or how to have the composition. Here you can see that for shallow water depth, which is the wave height less than 400 feet. Basically we also say this water depth classification in terms of non-dimensional forms, right, h by lambda. Anyway, so this is for people who don't have engineering, I mean ocean engineering background. Generally they say if it is of less than 400 feet. So basically in meters you will have around 130, right, 100 plus, right. So here you can see that for shallow you can choose a catenary, whereas for intermediate there is always a transition from catenary to your taut mooring, correct? And then for ultra deeper waters you don't go for catenary at all, right? Because if you are going to go for a catenary mooring in case of an ultra deeper waters, 5000 meters, for example, let us take the weight of your mooring line is 50 kg per meter, the submerged weight, right? 50 kg per meter in 5000 feet, you just imagine what will be the top tension. For example, this is my floater and this is the line which is, this is your top tension, fair lead, that's what we told, correct? If the water depth is going to increase, your fair lead tension will be very high. Why? Because the suspended length is increasing, correct? So you need to make a different composition such that this tension will come down, because the moorings you cannot avoid, sir, you must have it, correct? But then we find a way to reduce it, that's what at max, that's what we can do, right? So if your mooring line is 50 kg per meter and if it is around 5000 feet, so the top tension will be very high. So in that case what we try to do, instead of having a mooring line of with this property, with this weight, we try to come up with the different lines and then combine them, right? That can be done, correct? Okay. So that is why the chain, wire chain mooring composition is preferred. The reason is primarily aimed at reducing the top tension. If you don't do, and if you are going to have a complete as a chain itself, because of the self weight itself it will fail, it will start yielding, because of the self weight itself it will fail. So you need to find a different way. So that is why we have initial first part as chain, and then you will have wire rope, and then you will have a chain again. Okay, so now we will take a quick question, why we are going to have a chain on the seabed. So now we said that for deeper waters and ultra deeper waters we are going to have a different composition, correct? Chain, wire rope, chain, chain, polyester or chain, right? Again, why should you prefer to have chain at the seabed? You get the point, right? Here we are going to have a chain, here I am going to have a rope, polyester rope or whatever, again I am going to have a chain. What is the advantage if I am going to have a chain close to the seabed? You get the question, right? For deeper and ultra deeper waters, when you are having a mooring, it is not going to be a single item, it is going to be a chain, wire rope, chain. That we understand the reason. Why? Because to reduce the top tension, that is what we kept on saying, correct? So now the question is, why to prefer chain closer to the seabed? So here we said chain item is coming up, correct? And here again chain. Why? That is a question. Sorry? Due to friction. So abrasion resistance, that's right. So abrasion resistance. So when we have these moorings, they are going to be there for 20-25 years, right? They keep on, your floating body will keep moving, right? It will keep excurсing. So because of which your line will lift off and again it will make a contact with the seabed. They keep rubbing the sea surface. So you need to have some material that will take up this abrasion, right? So abrasion resistance, which is higher, your chain, because they are all rugged items, correct? So they can take this abrasion resistance. Okay. And now still we are not sure how much should be the length of chain, how much should be the length of wire rope, right? All these things we don't know. As of now what we understand is that moorings are an integral part of any floating structure, right? Primarily aimed at station keeping, correct? And depending on the water depth, it can be a complete catenary or a chain, wire rope, chain, right? And depending on the requirement, how much offset should happen, it can be catenary or taut. Okay. So depending on determine the anchor radius, so determine the number of lines and the size of mooring, determine the grouping and spreading. So these are some of the important things that we have to take care, and we have to, when you design, you need to start somewhere, correct? So if you actually see the floating structures around the world, this table basically says that for different water depth, what should be the radius to the depth, right? So you can see that when your water depth is very less, we told that catenary can be used because the top tension is not going to increase, right? Hardly, for example, 20 meters you have, 20 meters of, for example, assuming that 20 into some catenary factor 1.3, right? So let us put it this way. So you have a floating structure let us take we have 20 meters only, right. So we told that we will not go for a composition, we will go for a complete chain only, right. So now it is not your water depth, this is your water depth 20 meters, correct, but then we multiplied with some factor, what we call as a catenary factor, basically to account for the, from your TDP, it is not your just the vertical line, correct, it is going to be an inclined line basically. So there is a factor what we multiplied, catenary factor, so 20 into 1.3, correct. So now what should be the length on the seabed, that is a question. What should be the length on the seabed? If my length on the seabed is very less, assuming that your length on seabed, and if this floater is going to move this direction, quickly they will come in tension, right, and that load will act on your anchor, right, which you are not interested. You don't want to transfer more load to the anchor. Anchors are there to help you restrain it, but you should not continuously transfer the load. So again, depending on the type of anchor you choose, some anchors primarily meant to take both the horizontal and vertical loads, that is okay. But depending on, again, for example, drag embedment anchors, pile anchors, so depending on the type of anchors, so all these things has an hit on the other. If you start designing one, that will have a added advantage on the other, one will have a negative impact on the other, so you need to make a good trade-off between the different items, right. Okay, so now selecting the anchor radius, so we told that this is the anchor radius basically, correct, this is your anchor radius, correct. This anchor radius to the depth is not a fixed number, so depending on the water depth that will again change. Here you can see that for increasing water depth it is approaching to 1, you see it is approaching to 1, right, but then when you are dealing your floating structure in a shallow water, you cannot have your anchor radius same as that of water depth. For example, we told 20 meters, correct, so you cannot say that I will also have my anchor radius from, anchor radius is basically from here to where it terminates, correct, this is your anchor radius from your mean position, correct or not, you cannot have it that way. So you need to have an increased length on the seabed, right. So why you want to have an increased length on the seabed, because just in case your floater excurses, right, you will have a larger length that has to be lifted, then only, so that will give the restoring force for your floating body, right, so that is the main aim. Okay. So in summary, some key points to take into account are, for shallow waters the anchor radius is sufficiently large, it is understandable, because as your floater excurses it has to lift that much amount of chain, right, so that will give you the restoring force. Having a higher line length on the seabed ensures no uplift on the anchor. So there is no defined rule for choosing the anchor radius, so it depends on the site's water depth, so that is a point. Having less number of mooring lines may be cost effective, but it threatens safety, correct or not, if just a single point is connected, correct. For example, if there is a villain, if you don't put a single rope, correct, so 4 or 5 ropes are connected, the reason is, so you want to ensure that he stays there, right, the same way. So having less number of lines may be cost effective, but it threatens the safety. If the line length is smaller, there is less installation time, so in case of your taut mood condition, correct. So when we say taut mood, there is no line length on the seabed, that is what we mean. When we say catenary line, few meters of line is on the seabed, in case of taut mood there is no line length on the seabed, right. So in case of if the line length is smaller, you will have a smaller watch circle, right, quickly you will get a the resistance from the anchor point, right, where it is connected. So pre-tension is basically the winch tension in the mooring in the absence of external environment. So basically when we say the pre-tension, we basically mean what is the top tension without the presence of any load. For example, I have a floating structure, the same thing I am going to repeatedly do. So you simply have a line, correct, so this length is suspended, correct, so this is going to have a downward loading, because of which there is always some kind of a tension, correct. So this is what we call as a pre-tension in the absence of any external loading, right. So when you choose it, it has to be such a way that 10 to 20, these are all the thumb rules, so there is no defense, why should I choose this way, can I take a different number, you can always free to do, but then finally when you do other extreme analysis and other fatigue analysis, it has to comply with them. If you are able to satisfy it, you are good to go. There is no single solution, multiple solution exists for a given problem. Okay, I think this also we spoke about. And again when we have a, this is also a spread mooring only, correct. So when we have it, when you have a floating structure, you spread it over your complete floater, right? It is distributed on the floater, but then sometimes we prefer to cluster them, group them. When we say cluster, basically we are trying to group them, correct? So this is what you most of the time you see it for your floating offshore wind turbines or for any wave energy converters, all these things, because this is relatively easy to handle compared to this one, right? For example, if I am going to group it here, right, if I want to make any changes, it is easy for me compared to having a complete spread over a structure itself, right? And they generally come in, for example, in spar also you can have the similar items, and this is what we call as the internal angle. So this is generally 10 to 20 degree. So what is the angle between the lines, right? So all these things, so why 10 to 20, so there is no defined, but then so that is how the much of the conventions or the existing items are there. Okay, so now the mooring design process. So now we understand that a mooring line cannot be a single item, it cannot be chain, it cannot be wire rope alone. It has to come in combinations depending on the water depth, that's what we are saying. So in shallow waters we use chains, I think we addressed this question. In deeper water, then what happens if you use chain? What happens? Your top tension will be very high, because of the self weight itself it will fail. So in order to avoid it, we go for a combination, right? Chain, wire rope, chain or chain polyester wire, chain again. So what happens to the catenary shape and angle at the top? For example, if your weight is going to be very high, for example, we told 50 kg per meter, right? That's what we are saying earlier. When you, so what we mean is per meter length, what is the weight of your mooring line? That's what we mean, right? Generally, when you go and purchase it outside from a vendor, he gives the weight in air. So you need to find out what is the weight in water, right? Minus the buoyancy, you will get the weight in water. This weight, if it is going to increase, right, it will become, so instead of being it this way, it will become more of this sort, right, if the weight is going to increase, right. So what is the weight order of chain? So of course the chain will be higher, right, the chain will be greater always, wire rope and synthetic. So this is the order in which it will be there, right. So as of now we understand that moorings are an integral part. So again I repeat, just a quick summary, moorings are an integral part of any floating structure, whether you are going to deal with the floating offshore wind turbine, wave energy converter or oil and gas platforms, whatever it is, moorings are an integral part, primarily aimed at station keeping, right. Then what else we saw? What are the different types of mooring patterns, right, and for depending on the water depth, how to have it, whether you will have a chain, wire rope chain, this is what we have been saying, correct. So all these things comply with some standards, I think I have given it here, some reference codes basically. So primarily this is what we use, APRP2SK, design and analysis of station keeping systems for floating structures, and also other supporting documents also come in picture, the DNV JL OS 301. So the beauty of all these code books is that you will never get a straightforward answer. You read one thing, they always say take diversions will be there. You start one, they say that you refer that one. When you go there, it doesn't end there. They say you go and refer the other one. So but then if you are able to integrate them, connect all the dots, I think that will give a good clarity. So and also there is a quick summary about what are the different other codes that is relevant to that. We did not discuss about what is the material in which it is made, right? That's also an important question, right? So and also whether that material has to comply with some standard again. See, you have started with the mooring, right, it is made of some material, that again has to comply with some standard, right, and it has to be certified, then only it can be supplied for an offshore scenario. Okay.